Just a little bit more to go here on chapter 2. We got into really conversions, qualities, and as we talked about last time, dimensional analysis. Remember that when we do really conversion problems, which is essentially sort of dimensional analysis, we want to make sure that we do show the work where we can see the units really canceling each other out. We use conversion factors. And remember, the key to it is really opposites cancel. So by properly sort of putting in your units, kind of what's on top unit, what's on the bottom unit, you clearly, hopefully know what you need to do in terms of the calculation. And remember, everything on top gets multiplied, everything on the bottom, you go back and divide by. And pretty much if all the conversion factors there in the middle are metric to metric or English to English, then you really don't have to worry about the significant figures in those conversion factors. Remember, it's only really when you cross over sort of metric to English that you should look at it, except for a couple that we talked about, like the 1 inch is 2.54 centimeters. But for the most part, you can kind of lay it up there, and the original number is oftentimes very close, or the right number of sig figs that you should have. So I think we finished with the AM/PM example, I think, last time. So I think we're on this one. So why don't you take a couple minutes here and see what you come up with in this case. Again, we'll give you some maybe equalities that you can use to help you do this, and some conversion factors. So take a moment or two and see what you come up with here. All right, let's take a look. So here we're really starting with pints, and we want to end up in milliliters. So the pathway I'm going to go is pints to quarts to milliliters. And again, these would be the equalities that we could get for each of those sort of conversions and our conversion factors here that we will use. Remember, we don't use both conversion factors. Otherwise, that sort of undoes everything. So we will start with the 5 pints. Also remember that although it's not written as a fraction, if it helps you, you can put the 1 on the bottom there, and then you can clearly see that the pints in terms of units are up on top, which means that should help us pick the correct conversion factor here, which in this case should be the one on the left, as pints is in the opposite location so that they cancel. And that gives us 1 quart is 2 pints. So remember, if we stop right at this moment, the units of pints will cancel each other out. And we are left with quarts, which is close to what we want. But we do need to do one more conversion here. Again, as we talked about, you can get an answer if you like and continue on, or you could just continue on with the calculation. I'm going to continue on with the calculation. I should use which conversion factor there, the one on the left or the right? We should use the one on the right. Again, by doing this dimensional analysis way, we could clearly see our quarts are still up on top, and we do want to get rid of it. So we will use the one on the right there, which is 1 quart is 946 milliliters. Again, here the quarts will cancel each other out, and that's it. The only unit left there is milliliters. So we're going to take 5 times 946 basically, and we're going to come back and divide by 2. And it looks like we get something like 2365 milliliters. Now, in terms of sort of conversion factors, probably could ignore these guys. We would look back at this guy, and that's probably the one that's going to determine it, as it has 2, which means technically we should end up there. And we can write it as 2400 milliliters. Again, no decimal point. Or if you want to use scientific notation, you can do 2.4 times 10 to the 3. Any questions on that there? So again, as we talked about last time, in terms of what you need to show to get full credit, again, it is the bottom calculation, obviously with the answer to the right sig figs. You do not necessarily have to show all that stuff up there, but if it helps you, again, you know, you should show it. Any questions on that particular one there? Okay. All right. So it agrees with me as I wrote all over everything. There you go. All right, I think we've got one more here to go. So why don't you give it a try? You're stranded 125 miles away from home. You decide to walk 55 feet per minute. How many days would it take you to get home? Here's some equalities that will probably be some helpfulness to you. All right, take a minute or two to see what you come up with here. Okay, let's take a look, see how you're doing. So in this particular case, we are looking for days, which is obviously a unit of time. We have a distance, which is 125 miles. We have this, which is really a rate, right? And a rate is basically how far you go in a certain period of time. That's really the conversion that's going to allow us to go really from distance to time. But we do have an issue with it. And the issue is one unit of distance is like miles and one is in feet. So you do need to do some type of conversion to make sure that they're in the same unit. You can either take the miles to feet or you can take the feet to miles. I'm going to take the miles to feet, and that way I can use the conversion there just the way it is. So that's really where I'm going to start. Is I'm going to just try to get both of those sort of length measurements really into the same units. Otherwise, they really won't cancel. So the first thing I'll do is going to take the 125 miles. Obviously, I'm going to use this guy here as a conversion factor. My miles are on top, so I want to go opposite with my miles, which should go on the bottom, and my 5,280 feet up there on top. That will cancel out my miles. That will lay me up like 660,000, I think, feet, if I'm not mistaken. Really, all I've done is just convert the units. And again, it was necessary because really my rate here is in feet. Now we're good to go. Everything should cancel out correctly. Because that's really like a conversion given to you in the problem, you essentially can use it like a conversion factor in either direction. You know, you can put minutes on top and the 55 feet on the bottom and really just use it like a normal conversion factor. So carry my number down here, which is 660,000 feet. Again, here, feet are on top. So I am going to want to use that as this type of conversion here, where feet will be on the bottom. And that would give me 55 feet per minute. Using that rate, that's going to cancel out the distance. And now I'm in minutes, which is a unit of time. And that's good because that's what I'm looking for, some type of unit of time. Any questions so far? Now, again, it's really important here to set it up like this because now I could clearly see my minutes are on top. So to get rid of my minutes, I need to go opposite and go 60 minutes on the bottom is 1 hour. Again, the minutes would cancel here. And again, I can see my hours now are on top, which means I want to get rid of hours and go to days. That means I need to put my hours on the bottom and my day up there up on top. Hours will cancel. Again, I can't tell you how many times I've seen people, in this case, multiply the time instead of dividing, which is really what you're supposed to do. So really critical that you kind of set all that up. Basically, we're going to take 660,000 and everything on top there's 1. So you don't really need to multiply it unless you really want to. We're going to divide it by 55, hit equals, divided by 60, hit equals, divided by 24 and hit equals. And that's going to give us a 8.33 days, a nice relaxing walk for over a week. In terms of sig figs, because I believe that's what it was on your paper, that's 3. That guy is also 3, which means everything else in here is exact numbers. So we should end up with 3 significant figures on that. Any questions on that calculation there? Question on dimensional analysis, conversions. Again, you got to get into the habit of sort of setting it up, showing the units, and it really is beneficial to you. So like I said, it's very common. People will multiply when they should divide or divide when they should multiply. So just keeping all the units separate is a very helpful way of doing it. Any questions? Chapter 2 is density. So density basically refers to, or really sort of determines whether or not an object will kind of sink or float. For example, in water, if something is more dense than water, it will sink. And if something is less dense than water, it will float. Density really is basically the mass of an object to its volume is the density. And we can see here, we got things of different densities here. And obviously the guy to the top there should have the lowest density. The guy sitting there on the bottom should probably be the heaviest, or I guess the higher density is a better way of wording that. Now, if we have liquids and we put liquids together of different densities, they will basically separate out, right? So you'll have these different layers based on their densities. The more dense liquid would be which one? Yeah, the more dense guy would be down here. And the least dense, if that's a layer up there, would be up there. And obviously, if you put like something in there and it just kind of floated in that layer, that would say that this orange circle is more dense than everything above it and less dense than everything below it, right? And sort of where it would be. So we can calculate the density by taking the mass over the volume. It is a formula you should know. Density is mass divided by volume. We'll put a box around it. We also can solve for any of these things. So if we solve for volume, by the way, volume would equal mass divided by density, multiplying the volume to the other side and dividing back the density. And if we solve for mass, it would be volume times density. Sometimes people remember this by the DMV triangle. Everybody loves the DMV, right? Unless you have to go there. So density is mass over volume. Volume is mass over density, and mass is density times volume. That's how sometimes people remember it. Now, in terms of units for density, there's really a couple common units that we come across. For things that are solids and liquids, the units are grams per milliliter, or grams per cubic centimeter are the typical units that you have. A reminder that a milliliter is the same thing as a cubic centimeter, right? So they're basically the same. For gases, which we really don't get into density of gases, but typically speaking, if you calculate the density of gas, it's usually grams per liter. But like I said, in this class, these are pretty much your units that you will see pretty much for density, which is our grams per milliliter. You do, again, need to know that equation. You need to know how to properly rearrange it. And the sort of value of density, the number that you get always stays with the grams part, and it's always like 1 milliliter or 1 cubic centimeter. So if you ever calculate the density of something, it always stays, the number stays with the grams part of it. Any questions on that there? So as I said before, most things have in their solid phase a higher density because everybody's packed in really tight to each other. One exception is our good friend water. By the way, when we think of water, if you ever need to use the density of water, that's usually the value that you could use, 1 gram per milliliter. By the way, the density does change with temperature, but if you're doing some type of problem, it's almost a safe bet to go with 1 gram per milliliter for the density of liquid water, unless it specifically mentions something about temperature, but it does actually fluctuate with temperature. The one exception to that is when we have water and we have ice in our drinks, our ice usually ends up where in our drink? The top, which means it's less dense than the liquid water. Ice is water, right? That's H2O. So it's obviously liquid water, H2O. And it's one very unusual property of water is that when it actually comes together in the solid phase, what ends up happening is all the waters really come together, and it ends up happening when they bond to each other. Looks nothing like that, but it creates a big empty space there in the middle of all the water molecules. So what it actually ends up doing is increasing the volume of it. And if you think about density, which is mass divided by volume, for increasing that number, the density will then become a smaller number, right? Small number divided by a large number, smaller number. So actually water is, ice is, as you can see here, about 0.9 versus 1 gram per milliliter for liquid water. And again, it just has to do with how water comes together in sort of the solid form, creates a lot of empty space and increases its volume. And that's why, it floats. Just like if you take a Diet Coke can and a regular Coke can and put it into a sink of water, will they both sink? Will they both float? What do you think? Will they do one of each? Will one sink and one float? The answer is you should go try it. No, I'm just kidding. It's a good party trick. One will sink, one will float. Which one will float, you think? How about which one will sink? The regular one, right? The regular one will sink. The diet soda will float. And that is because in regular soda, there is sugar, right? And like Diet Coke, there is artificial sweetener, which they need to put a lot less than there to get the effect. And then it's a good little party trick. You know, Diet Coke floats. Regular Coke basically will sink because of that. As I mentioned before, our cubic centimeters is a very common volume. And there's really sort of, you know, a few different ways that we can get volume when we're doing density. One is very easily, it's just simply reading the meniscus, right? And taking an actual volume reading. The other one obviously is more for solids, where you would measure the length times the width times the height. And again, if you measured each of those in centimeters, that is again how we go from length to a volume. That is cubic centimeters. So that's a very common way that we kind of do it. Another very common way that we measure volume, and I think we might have a slide coming up on it, but maybe I'll jump the gun here, is basically if we take something like water in a container, bless you, and we take some type of solid and we put it into that container, like a graduated cylinder. Oh, no, it looks more chemistry-like. There it is. What's going to happen to the water level in there? Will it go up? Will it go down when we put the solid in? It should go up, yes. And what will happen is as that solid goes in there, the volume will go up. And a solid object will basically displace a volume that's equal to its own volume. And we could very simply do a calculation to figure out the volume of the object by basically taking the volume where we ended in volume. So this is a very simple approach to find the volume of the object, which is final volume minus initial volume. This is what is sometimes referred to as volume by displacement. And that's a very, very common way that we can determine sort of the volume of a solid object by just simply dropping it into water, taking a couple of readings. So those are three very common ways, you know, when you're calculating something like density to get the volume of liquid, a solid. Any questions on that there? Here's some density of some common things. Like I said, that 1 gram per milliliter, which is pretty much a safe unit or safe density to use for water. Obviously, anything that's heavier would sink. So, you know, they give you lead boots, as they used to say in movies, right? And throw you into the water, you sink, right? Because lead is 11.3. And obviously anything less than that, less or higher than 1 will be that. I think we're gonna skip this here. So here's our volume by displacement, as I mentioned before. Here's a prettier picture of that. And it's a very common experiment that you guys don't do because they skip the density lab here. But you usually take something like a graduated cylinder. And again, just doing that difference in volume will allow you to do it. It is important when you do a calculation like that, that you do, again, still follow the significant figure rules like we talked about. Clearly, if you're going to do the density here, which is our mass in this example, and this is our volume, remember that you would most likely do the bottom part first, which means we're subtracting, which means we should go to decimal places to get our number for our volume. And then the last thing you would be doing is dividing, which would be 68.6, which is 4 significant figures, by 9.5, which is 2 significant figures. And obviously that is, in this particular example, why they ended up with 2 significant figures in this particular case. So again, in sort of density, you do a lot of times a combination of subtraction with division or multiplication, because again, that's a very common way that you find the volume. So you just want to make sure, as we talked about, that you sort of keep track of everything as you go through there. All right, so why don't you take one here. What is the density of a 48-gram sample if the water level in a graduate cylinder went from 25 to 33? Calculate the density in grams per milliliter. All right, so in this case, obviously we're dealing with density, so you want to think about the formula here. We have 48 grams, which is a mass. We have an initial and a final volume, which means we can obviously calculate the volume. So really we have sort of everything we need there. This again is a volume by displacement. So initially our level was here. After it went in, it was sort of here. That difference between those two would give us our volume. So the volume of the object in this case would again be our final volume, which is 33 milliliters, minus our initial, which is 25 milliliters. And that is 8. What should it be? Should it just be 8 like this? Technically it should be 8.0, right? 1 decimal place on each. And that is really critical for the rest of the calculation to make sure that you end up with the right sig figs. Now we really do have the actual volume. We have the mass, so all we have to do is plug in here. So 48 grams divided by 8.0 milliliters. Again, our calculator is going to lay us up a 6, but it should be 6.0 here. The last thing we're doing is dividing. That's 3 sig figs and 2 sig figs. Means our answer should be 2 sig figs. And in terms of the units, they do not cancel. So the number stays with the grams and it's per milliliter. Yeah. So again, the number always stays with the grams part and it's 1 milliliter. And it would be obviously 6.0 grams per milliliter. Any question on that one there? Like they did in that example, or you could do it separately, but I do need to see both parts of that. Yeah. Other questions? Okay, so if we do have something like the density, we'll take the number we just got there, which was 6 grams per milliliter, and we were given a density and a problem, we can again use it like a conversion factor, and it would work just like all the others. So for example, if we're using that density we had on the previous problem, we could really write 2 conversion factors to use it. It's sort of like a dimensional analysis sort of problem, or to kind of set it up in dimensional analysis so you can see the units canceling. And you definitely can use it as a conversion factor. So why don't you give one a go here? An unknown liquid has a density of 1.32 grams per milliliter. What is the volume in milliliters of 14.7 grams of liquid? All right, let's take a look. So obviously, again, we're dealing with density, which is our mass divided by volume. So if you're not sure where to begin, they obviously gave us the density. They also gave us the mass. So, you know, it would make sense, obviously, to solve for volume in this case. As we talked about, we would multiply the volume to the other side and bring the density divided back, and we will get mass divided by volume. Now, you could just plug and chug into that, or you could kind of do it more dimensional analysis way. Again, we could take the density and really use it as a conversion factor of 1.32 grams per milliliter, or you could do a milliliter is 1.32 grams. Again, if you take more of the dimensional analysis approach, you hopefully won't mess up on what you're supposed to do in terms of rearranging. You just simply got to do what we did with conversions. I see grams are up on top, which means my grams need to be on the bottom, which means I should use this guy, which is essentially dividing by the 1.32 grams. And if we do that, we would take our 14.7 divided by 1.32. And again, on our calculator here, 11.13636636 and so forth. And that would be milliliters. This should end up at what number of significant figures? Should end up in 3. We're really dividing. So again, 3 on top and 3 on the bottom, which means we should end up right about there, which would be 11.1 milliliters. Any questions on that one there? Yeah. No, you really shouldn't put 11.10 because then it would have how many significant figures? It would have 4. So it would be technically wrong in the sense for significant figures. In that case, yeah. Other questions? Yeah. it should come out the exact same because that's basically what we did. We basically just divided, right? But again, sometimes when people rearrange, you know, again, they get into a situation where maybe they're not 100% sure if they should be dividing or multiplying or, you know. So again, if you take more of a dimensional analysis approach, you could just approach it like a conversion factor. And just like we did before, units on top, units on the bottom to cancel. And you probably will kind of do the math correctly in that sense. So sometimes it's a safer way per se than rearranging certain formulas and stuff. But absolutely you could do it both the same because mathematically it is the same, obviously, whichever way you do it. Other questions? All right, we'll go through 5 things here and they agree, so that's good. All right, John took 2 teaspoons of cough syrup for a cough. If the syrup has a density of 1.20 grams per milliliter and there is 5 milliliters in a teaspoon, what is the mass in grams of the cough syrup? We do have density mentioned, which is mass over volume. Obviously, we do have the density given to us. Teaspoons is a volume, so we do have the volume given to us. So again, if you're not sure, we should be aiming for mass here. And again, the mass would be volume times density. We do have a little bit of an issue. Our volume here is in teaspoons and our volume here is in milliliters. So again, we're going to have kind of like the same issue we had with our feet and miles in that previous problem. We do have to do a conversion, which is why they gave us 5 milliliters is 1 teaspoon. So I'm going to convert the teaspoons into milliliters, and then I really could just use the density like a conversion factor to solve for what I'm looking for. So if I take my 2 teaspoons, again, to cancel that out, we want 1 on the bottom there and our 5 milliliters there. Up on top, teaspoons will cancel. That gives us 10 milliliters. Now we can use our density again if you want to do more of a dimensional analysis approach as a conversion factor. Again, either way. In this case, we have 10 milliliters. And again, we can see milliliters up on top, which will tell us we do want to use a conversion factor like this, which is essentially multiply it like we have here. And if we do that, we end up with 1.20 grams per milliliter. Milliliters cancel, and we end up with our 1.2 times 10 gives us 12 here. And it is 12 grams. And the significant figures here should be, it actually should be 12. I did not go correct sig figs here. I got put an extra decimal there, but really the 0 shouldn't be there. It actually should be 10 because both of these guys are 2. And then obviously here, we wouldn't need that. We got 2 times 3, which should end up with 2. Yes, I wrote an extra 1. I cleaned it up at the end. I think that's the important part. Any questions on that calculation there? So again, really the key here is, you know, you want to watch units, and sometimes people are so quick just to throw it into the equation that they don't see the units are different and you won't get the right answer. Again, another reason why maybe the dimensional analysis approach is a good one. So you could clearly see, whoa, I got teaspoons here, maybe I'm starting with, and that's clearly not going to cancel. So, you know, it sometimes will help you catch some of those common mistakes that people make. Any questions on that there? There we go. All right, any questions on density? All right, where you're not going to worry about specific gravity, so don't worry about any of those slides. Say specific gravity, and that will be chapter 2. Yes, so we're up to chapter 2 here. As I put out an announcement last week, I posted up a pre-recorded lecture for chapter 3. We got obviously quiz coming up on Wednesday on chapter 2, right? At the very beginning. All of chapter 2, including the stuff we talked about today, which is basically density, I think is what we added in there. We got a holiday coming next Monday, right? So again, I posted that chapter 3 so we could try to stay a little bit on pace here as we got some dead time coming up here in terms of holidays and quizzes. So we're going to go now to chapter 4. Again, you are responsible for chapter 3, which is energy. And obviously it's going to be on the exam. So make sure you look over the video, watch the video. And if you have any questions, obviously during discussion or something like that, I'd be more than happy to answer any of those questions. But just to try to keep us here on pace. Here's a little bit in chapter 4, a lot going on in chapter 4. We're going to talk about the atom. We're going to talk about kind of the structure of the atom. We're also going to talk about a little bit of some of the experiments that sort of led us to the understanding of the structure of the atom. We're going to talk about protons, electrons, neutrons, and we're going to finish it up with electron configuration and how electrons are in the atom. So there's a lot of stuff here in chapter 4. So let us get going on that. Obviously atoms and elements. So I think we've touched upon it earlier on, but remember that, sort of elements like we see here on the periodic table, they're really as far back as you could go in terms of substances. They're the basic sort of building blocks of everything. You could think of elements, kind of like the alphabet. There's only so many letters in the alphabet, right? But different combinations give you different words, different meanings. Same idea here. There's only so many elements, but different combinations of those guys does give you really different sort of molecules, compounds, and so forth. Now, the atom is really the basic unit of an element. It's really our basic unit of an element. And as you may know, and as we'll talk about here, an atom is really composed of, even though it's really, really small, it is composed of 3 smaller particles, which are sometimes referred to as subatomic particles. And those are protons, which are positively charged. Those are electrons, which are negatively charged. And those are neutrons, which have no charge. So the atom basically represents, it's the representative unit of all the elements. And within this really small atom, there's really sort of that internal structure that's really made up of these 3 particles. We'll talk about where they're located and all that good stuff in this chapter. Now, when we talk about elements and symbols, it's important to know the symbols. And if you look at the periodic table there, which I can't see it, so I'm assuming you can't really see what it's on there. But if you look at a periodic table, I know it's like a physics room. That was the one periodic table they gave us. So that was good. They're like, "What? You're supposed to be on the 3rd floor, not down here." When we look at the elements, they all have symbols, and they really have 2 sort of types of symbols, or 2 ways that they're sort of illustrated. They're either illustrated with a 1-letter symbol, like for example, K, which is potassium. And if it is a 1-letter symbol, then it is capitalized. So you want to always capitalize it. If it is a 2-letter symbol, like aluminum, it is the first letter capitalized. The second one is not. So those are sort of the rules for sort of how the symbols are. 1 letter always capitalized, 2 letters, first letter capitalized, second one not. And it's really important to make sure that you do follow these rules. Somebody that does write sort of in capital letters, which I know some people that do that, there is a difference. For example, if you write capital C, lowercase o, and you write capital C and capital O, it may seem like there's a difference, but this guy here is an element that is cobalt. An element written like this. This is carbon monoxide, and it is very different. So it's really important to, follow those rules, especially maybe you're somebody that writes everything in capitals. Definitely don't want to do that. Definitely when you're doing the symbols. Now, do the names come from a wide variety of sources? They do. They come from, historical sort of names of people who sort of found them or discovered. Latin names, all kinds of names is where things come from. Hence why potassium here is K, not P, right? P is actually phosphorus. Iron, for example, is Fe, right? That's iron. Again, capital F and lowercase e. Copper is Cu, right? It's copper. As we saw earlier, zinc is Zn, that's zinc. Sodium is Na, right? So that is sodium. So some of the symbols, you know, may not name if they per se. Obviously, you might think sodium should be S. So, you know, it's really important to sort of get a feeling for the symbols and the names. It's going to be very helpful as we go into sort of naming, which is or so. You know, you should really get an understanding of the symbols and names. When we talk about naming, there's a lot of rules for how to properly. And if you're still sort of struggling in terms of, you know, what symbol goes with what, it's just going to make it really difficult. So I would take some time and learn a lot of the symbols. I know maybe on the homework it says, or I used to say maybe like 1 through 40, but, you know, for the most part, if you look at the periodic table, you know, we really do sort of deal with a lot of the elements sort of on this part of the periodic table. You usually can see like a staircase sort of coming across. We usually deal with the elements up in this region and over here. A lot of times we don't necessarily deal with a lot of the element names sort of in this block, or there's like 2 rows on the bottom. We don't really deal too much with the guys on the bottom except for uranium. And then there is another sort of block over here. So you'll get probably the idea as we go through examples and stuff, you know, which sort of elements and stuff sort of come about. But, you know, you can almost think left side, right side, kind of the top-ish to the right down is a lot of the stuff that we very commonly will see in terms of elements and understanding those symbols. Elements, as I said, are pure substances, which are all things are really built upon. It is as far back as you could go, so you cannot break elements into anything smaller. There are some elements that do come as molecules. So there are certain elements that come as what are referred to as diatomic molecules. And basically, I hit something there. Oh, there we go. Diatomic molecules is H2, O2, N2, F2, Cl2, Br2, and I2. These are all what are referred to as molecules. So what is the definition of molecules? A definition of a molecule is the combination of 2 or more atoms. Now, those atoms could be from the same element. Those atoms could be from different elements. But in each of these cases here, these guys are all elements. And they're all also considered diatomic molecules and molecules because basically when you have hydrogen, you got 2 hydrogen atoms that are together. You have oxygen. You got 2 oxygen atoms that are basically together. So they meet the definition of a molecule, which is why they're sometimes referred to as diatomic molecules. But they are also referred to as elements because, for example, H2 is only made up of hydrogen. Oxygen, O2 is only made up of oxygen. So they are elements and they are also molecules. Now, sometimes people get really confused with the idea of molecule maybe and a compound, which I think we'll see a little bit later on here. But a compound is the combination of 2 or more atoms. Kind of sounds very familiar. 2 or more atoms from different elements. And that is the major difference between a compound and a molecule. A molecule is really like a generic definition. It doesn't really matter. It could be atoms from the same element together, like we see here. We could also have something like water, which is 2 hydrogens and an oxygen. That is also a molecule because it is 2 or more atoms together. And this guy is also a compound because it is 2 elements together, 2 or more elements that have come together, hydrogen and oxygen. Is H2O an element? The answer is it is not, because it is hydrogen and oxygen, two different elements together. So something like water could be a molecule because it meets the general definition of I got two or more atoms together. It could also be a compound because it meets the definition of two or more different elements that have come together. It does not meet the definition of an element because there are two or more elements obviously present. Something like H2 is an element because it's all hydrogen. It is also a molecule because it is two or more atoms that have come together, but H2 is not a compound because it is only made up of the slight difference meanings, and sometimes people get really confused about those meanings. So the best way to think about it is, like I said, you can think of a molecule. It's really just like a generic definition. All you simply need is two or more atoms together. Doesn't matter if they're the same, doesn't matter if they're different. That would be, that's a molecule. For a compound, you got to at least have two or more different elements involved for it to be a compound. And again, that's a little bit more of a more specific definition, I guess, of what's coming together. Any questions on that there? So again, here's from your book, some of our symbols and our elements. And again, you should get familiar with some of these. Again, uranium is probably the only one on the bottom there that, you know, we will see a lot, but definitely chlorine, magnesium, you know, those are some that we definitely see. Some iodine as well. You know, we see those guys a lot. As I mentioned before, again, you want to make sure that if it's a one-letter symbol, we use just a capital one, and if it is two, capital, then lowercase. So there's our carbon, our sulfur, our nitrogen, hydrogen. These are all, you know, symbols that we really do come across a lot as we kind of go through things. By the way, mercury is Hg, so that's one that pops up a lot. Lead, by the way, also pops up a lot. That is Pb is lead, so that is lead. Let's see. Antimony pops up occasionally, Sb. Let's see. Okay, I did copper, I think, before. Silver is one that pops up a lot. Silver is Ag, so silver is one. And again, some of these, you're like silver Ag, it makes sense. But again, they are named for a wide variety of things. That's how we get things like California, Bellium, you know, they're named Liam, you know. Or again, like I said, standing of these symbols and their names, especially when we get at that naming chapter, is going to really help you out a lot. All right. All right. As you can see here, as I mentioned before, this is again where some of those symbols sort of come from, you know, sort of their Latin roots and ancient sort of names. Again, why gold, by the way, is another common one that we do see a lot, which is AU is gold. All right, so looking at these, we want to write the correct symbols for this. And again, you may not be familiar with yet, but iodine is I. Iron is a two-letter symbol. Sure, we capitalize and then lowercase with the Fe. Magnesium is Mg, right? Zinc is Zn, and lithium is Li. Yeah. So again, make sure you start getting a handle on those before we get to naming. All right. So let's just go through some of these here. P is phosphorus. Ar is argon. Is actually manganese, not magnesium. So Be is beryllium, and then K is potassium. I think we have it on the next slide, so much better writing than I did. Any questions on symbols, elements? Now, as you can see here, most of the, by the way, a couple of things when we talk about sort of our elements off the periodic table, most of the sort of elements are what are referred to as being monoatomic, which basically means, as you can see here, kind of comes as one thing together, you know. And again, those other 7 that we talked about are diatomic molecules, which come as 2. By the way, also, if I had a piece of iron metal by itself, does it have a charge? It does not. So that is some misunderstanding that a lot of people have, is if you have any type of element by itself, uncombined, no charge. Actually, as we'll talk about, things really only gain charges when they start to combine together. Basically, is when things gain charges. So if you had something, you know, like iron or a piece of iron metal, it basically would be no charge or anything associated with it. So let's talk a little bit about the structure of the atom. As I mentioned before, the atom really is sort of your basic representation of the element. It has that internal structure, as I talked about, which is even smaller, those subatomic particles of our protons, electrons, and neutrons. And it really is sort of your basic representation of elements. As far back as you could go. Each of these guys are really aluminum atoms here that we see in this roll of aluminum foil. Now, an early idea of sort of atoms and the understanding of atoms came from a guy named Dalton. And John Dalton came up with what is referred to as Dalton's atomic theory. And these are the main parts of Dalton's atomic theory. And a theory is something that may not always be correct in all aspects of it. Some parts of it may be found later on to be not so correct. And that's really the case with Dalton's atomic theory as well. Some things are sort of correct. Other things later have been found maybe not to be so correct. First off, let's take a look at these 4 parts to it. First off, he said that basically all matter is made up of tiny particles called atoms, which obviously, you know, that's all good. He also said that all atoms of a given element are identical to one another, and atoms of different elements are different from one another. And this actually, this part here, that all atoms of a given element are identical to one another, is something that was basically later proved not so correct. And with the existence of, as we'll talk about also in this chapter, what are known as isotopes. And what isotopes are really the same element, but they have different mass. Which obviously, as we will talk about, if they have different masses, then they obviously cannot be identical to one another. And they have different masses, as we'll talk about, really because they have different numbers of neutrons, which also means that they have different numbers of neutrons. Those atoms cannot be identical to each other. So later on, it was sort of proved that that's not so correct with the existence of isotopes. But the other part of it is sort of correct. You know, if you have a iron atom, it is going to be different than, say, an aluminum atom in terms of protons, electrons, and neutrons that are there. Atoms of 2 or more different elements combine to form compounds, and that is true. That, again, that's what we were talking about a second ago. That is really your definition of a compound, is you got to have 2 or more atoms or elements coming together to do that. A particular compound is always made up of the same kind of atoms and the same number of each kind. You know, for example, that also is correct. You know, you've got something like water. No matter where you get the water, it's always a combination basically of 2 hydrogens with every 1 oxygen, which is essentially the combination of, for every 8 grams of oxygen you got, 1 gram of hydrogen comes along with it. So that sort of combination is true. He also said that a chemical reaction involves only the rearranging, separating, and recombination of atoms. We never create nor destroy atoms in a chemical reaction. And as we'll talk about when we talk about not bonding, but balancing, that is the purpose of when we go, hey, if I started with like 4 carbons over here on this side, I should have 4 carbons really on the other side when it's all said and done in terms of the reaction. The difference is those carbons may be in different compounds on the other side, but we will still have really the conservation of those elements because we will not lose anything. Because in the basic chemical reaction, the only thing that really happens is everybody on the starting side breaks apart their bonds. Everybody reassembles on the product side with new bonds. And it's really just the electrons involved in that. And as we'll talk about, because only really electrons are involved, we never change any element to new elements or anything like that. So we always have sort of that conservation of the elements when we do a chemical reaction. If you do a nuclear reaction, you do not have that conservation because all you're doing is actually changing one element to another element. So, but in normal chemical reactions, like we pretty much talk about mostly at all in this class, is, you know, we have that conservation of elements because it's really just electrons involved. A little bit about the subatomic particles. As I mentioned before, we have our protons, our electrons, and our neutrons. Again, our protons being positively charged, neutrons having no charge, and our electrons being negative. Now, one important sort of aspect of sort of help people understand sort of the nature of the atom and help with experiments is a very simple concept that we see a lot in chemistry, and that is much like in life, opposites attract, right? Which means much like in life, if you're around 2 positive people, nobody wants to be there. That's just too cheerful, right? You're around 2 negative people, nobody wants to be there either, right? But if you get a positive person, negative person, you know, they sort of balance each other out. And it's really the same idea in chemistry. And it's a really simple principle for a lot of things that we deal with, which is essentially if you have anything that has sort of the same charge, they repel each other. They do not want to be near each other. So if you get something that's positive near positive, it doesn't want to be there. If you have something that's negative near negative, it also does not want to be there. But if you get something that's positive near something that's negative, they will be attracted to one another. So we see that a lot with sort of the experiments that were done to understand sort of the atom. We also see it a lot in bonding and ionic bonding and opposites attract and all that kind of stuff. So much prettier picture, I suppose, than what I just drew there, but our same idea there. Our same like charges will go opposite, and obviously our attractive forces come together. This, as we will talk about in a later chapter, is really the basis of a type of bonding, which is known as ionic bonding. And that is really the combination of something that's positive element, basically, or ion, with something that's negative, and they come together, and it's a really, really strong attraction. And typically when we put something that is positive and negative together, the strength of it does increase with like the charge. So what I mean by that is if you had something that was +1 and -1 and they came together, and versus something that's like +3 and -3 coming together, the +3 -3 would be held together a lot tighter or stronger than something that's +1 and -1 coming together. So actually the strength of that opposite sort of attraction increases as sort of the charges increase on those guys. It gets those guys in there really tight and they hold on to each other pretty strong. So really the first really big understanding of the atom was really with the invention or the cathode ray tube. And that is what is sometimes referred to as a Crt tube or a cathode ray tube. And it was really used a lot to really explore electrons. It was very big in sort of the understanding of electrons. You may be familiar with the Crt tube, but basically a Crt tube is a tube, hence the name. There's a positive side and a negative side. And basically there's a stream of negative like electrons that would be heading towards the positive side. And a lot of times they'll put something up here where it kind of fluoresces as it hits there. You may be familiar with it if you maybe have an older TV that has sort of a back on it. Not a flat screen, like one of those TVs, you know. I got a couple of those though. You know, your parents said, don't sit in front of it because it's shooting you with something. Yeah, that's true. That was their picture tube. That's basically a cathode ray tube. Maybe even have an older style computer monitor. I got one of those around as well that also has sort of that big back on it as well. These guys obviously don't, these sort of flat screens, but those are CRT monitors, and you know, they're basically these sort of beam of negative electrons being shot at it. So what Thomson did, he did a cathode ray experiment. He was able to figure out the charge to mass of an electron. And it was really followed up by another guy who did an experiment which was known as Milligan. He did what was referred to as the oil drop experiment. And basically, in the oil drop experiment, speaking of sort of opposites attract, is he had sort of an electrical field, and he basically shot in there droplets of oil that he basically sort of heated up. And he was able to really have the oil droplet just kind of hang there, basically. So normally it would drop, it would actually pick up a charge as a result of that. But he was able to really dial in the electrical field to get the oil droplet really to stay there. And what he was able to do was to figure out the actual charge on an electron. So these two guys did some really good experiments in terms of electrons. And from those two experiments, they were able to determine the mass of an electron, which is 9.09 times 10 to the minus 28 grams. That is a big or small number? It's a really small number. That's like this was really big sort of advancement in the understanding of the atom. It really helped understanding sort of the electrons that were there. And it was always believed that the atom was electrically neutral, which means that if it has these electrons which are negatively charged, there had to be something in the atom that was positively charged. So along came Thomson, and he came up with this model of the atom, which is known as the Plum pudding model. That's a dessert of pudding with raisins in it, basically. And he said, well, that's the atom right there. So he thought that the atom was this sphere of positive charge. So all that red is positive charge, really spread out all over the atom. Embedded inside, like his raisins in his dessert there, were the electrons. And he felt that the electrons were embedded inside. And he also felt that most of the mass of the atom was the electrons. So this was really an early model of the atom, and it sort of fit with the idea of we got to have it sort of neutral, and we got all this positive charge really spread out all over these negatively charged electrons that are embedded inside, and it makes up barely the most of the mass of the atom is those electrons. And this really was sort of the accepted model of the atom until the really next big experiment came along that helped us truly understand the atom. And this was the gold foil experiment. So Rutherford did what is referred to as a gold foil experiment. And what he did was he basically shot alpha particles, which are radioactive positive particles. They're really helium, if you want to know the truth. They're really the helium nucleus is really what they are. But he took really pieces of gold foil and he shot these alpha particles at it. So his idea was this, and what he thought would happen was, obviously, as we saw in that previous picture, based on the model, we have all this positive charge there. We have these sort of electrons that are embedded inside. And what he thought was he was going to shoot these alpha particles at it, which are positively charged guys. They're heavy. They're moving really fast. So it's kind of like, you know, if we held this paper up, somebody held it on both sides really tight, right? And this was like all my positive charge. And I took like a pen and it was moving really fast, right? You would expect it probably if both sides were held really tight. that the pin would be able to pop through, right? And there would be some deflection as it kind of goes through it and pops through the paper. And that's really what he expected to happen. He expected these positive particles, because they're hitting something that's, you know, kind of densely positive all over or spread out all over, that the alpha particles would go through, but there would be, you know, some bending that would sort of happen as it sort of goes through the mush of the positive charge and it kind of bounces through. And what he actually found was sort of surprising when he did this. He found that most of the alpha particles went right through undeflected, which means when he actually shot them, it just kind of sailed right through, no problem, those alpha particles, which means if they sailed right through, they hit what? They actually hit nothing, right? If you shoot something, there's nothing in the way, it's just going to go straight through, no problem. But really what surprised them was every now and then, kind of see on the screen, a alpha particle, these really large angles, shot out every so often. So if you have these really fast moving, heavy sort of alpha particles, which are positively charged, they get bounced off at these really large angles. Type of charge. They had to hit something that was very positively charged, right? Same charge, they don't like to be near each other. So what accounted for when we see these alpha particles bounce around at these really large angles is it had to hit something very positive. So what that essentially meant was when they think about sort of the plum pudding model of the atom, they had to sort of rethink about it and go, not so correct. We kind of have to throw out that model based on the results of what we just saw. And based on the result that the atom is mostly empty space, which is why most of the particles sailed right through, no problem. But it also contains a dense positive core, which is, as we see here, known as the nucleus. And out from the nucleus, we have our electrons moving around in that sort of empty space, if you will. So in that empty space around the nucleus, we have our electrons moving around. And another really major difference between the plum pudding model and really this one, which is the modern version of the atom, is that most of the atom's mass is the nucleus. And that is because, as we will learn, basically in the nucleus, we have protons, which are positively charged. We also have neutrons, which have no charge. And we have electrons out from the nucleus flying around. Do electrons fly in pretty circles? The answer is no, they do not. They travel randomly about the nucleus in that empty space. There is an attraction between the electron and the nucleus because the nucleus is overall positively charged because it has protons. Electrons are negatively charged, and they kind of are tied to them as they're flying around. Also, why not all the electrons decide to leave, because they're kind of attracted to the nucleus. Also, why, as we'll talk about, why some electrons are involved in bonding and others are not. Any questions on that there? All right, we will lay it up there.